Welcome to breadboarding. Almost 40 years ago, Compaq brought out the DeskPro 386 that was one of the first Intel 386 computers, and they also published a lot of technical information including schematic diagrams. And what I'm actually setting out in this project to do is to rebuild the Compaq DeskPro 386 on solderless breadboards. Now this is an image of the motherboard of the original DeskPro 386, and you can see the 386 processor down here. It's pretty complicated, largely made up of standard TTL logic chips, and there are also a number of programmable logic devices, or PALs as they were known back in the day. Now, we've already built our breadboard adapter for our 386 processor in some of the earlier videos, and we've tested that the processor is basically working, and also covered in the previous video the schematic diagram in KiCad. So this is your processor, but there are a number of programmable logic devices that we actually need to get working before we can start hooking up the various address buffers and data buffers, which is the next step of the project. And so in fact there are a number of programmable logic devices here, 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 and one here as well. So what we're going to be covering in this video is looking at the background to these programmable logic devices, or PALs as they are known, and looking at how we can use the Compaq design documentation to program them. And if we have a look at the design document, so this is the internal design document that I covered in earlier videos. There will be links for all of these in the description below. So this shows the layout that I just shown you earlier. And this is one of the PALs that we're going to be looking at. So this particular one is the data buffer enable logic. This one happens to have a couple of tricky bits in it, and also it mainly fits on one page. So this video is going to be covering converting the PAL designs, which are defined in PALASM, which was a very early language used to define these, and we're going to be converting these over into CUPL, which is the language used by the current microchip WinCUPL II, which I covered in a couple of videos ago. So this is video 9 of the Breadboard 386 PC, and we're covering the PALASM PLD conversion to CUPL. Now, I did briefly cover the PALASM files, and I covered them when I showed you the files which have been uploaded onto GitHub. So all these converted files I'll be showing you today will be up on GitHub for the next couple of days. Now, I'm not going to go through the exact process here because I've largely been made irrelevant, but there was a little bit here that there was this if syntax with a test condition just before a particular pin. And I translated this as that we need to include this rule in each of the conditions. That turned out to be wrong, and that was partly assisted by Copilot, which also told me the wrong things. Now, this has been quite an exploration to get to the bottom of this, and I'm just going to share with you a few background bits now to work out how to convert these files properly. So as I was looking for more information on the conversion of PALASM, then I came across an early version of the CUPL manual. This was for the DOS version, not the Windows version, and it actually alluded to a particular utility that would actually convert PALASM files into CUPL, and in fact the PTOC utility is what will actually do that. So rather than having to worry about changing the differences in syntax, then this would largely do it all for us. Now I also managed to find the PALASM II user documentation, for which there's a link there, and it did actually have an appendix, the differences between version 1 and version 2 of PALASM. Now we're using PALASM version 1, which is what was used on the Compaq DeskPro. And there were a couple of sections in here, some of the limitations, shorter names, but one of the main things here is the if condition was used to enable 3-state output. So the syntax that I showed you with the if condition on the earlier slide, this is actually used to configure the output enable function on the pins. And this also covers that the version 1 files have a fixed definition, whereas version 2 upwards is a bit more flexible. And I did also manage to find the PALASM version 1 file as well, and this actually says it a little bit more explicitly. So if brackets tells ASM the output within the parentheses is to only be output when this is true, otherwise it will be high impedance. So this is the output enable term, and it also covers some of the other syntax as well. So exclusive OR, for example, is a colon plus colon. And when we look at the test vectors that we'll be spending quite a bit of time looking at during this video, then it only dealt really with a low, a high. So this would be used on either on input to give it a 0, or check that the output was low on an output, and high, and an X for if we don't care. However, a little bit later on in the document, there was actually some information that really an X is entered as a low signal, and similarly an output is treated as low. So in particular, if we are using the output as feedback into another part of the simulation, then it would be treated as low, and this becomes important a little bit later on. I also then had to check the datasheet. So when we actually look at the definition, you'll notice at the top that there's a PAL16L8A. Now this actually tells us exactly what type of PAL chip it is, and the PAL chips are a lot more limited. And in fact, there are different configurations of them, and you'll see there's an R6 and R4. So rather than having a generic chip that would be capable of doing everything like we use with the current Atmel microchip ATF series circuits, then these ones were single use only, and you had to get them in certain configurations. Now the one that we're dealing with has got 10 dedicated inputs. We've got 6 combinatorial outputs and another 2 combinatorial outputs with up to 7 product terms. But in fact, only the 6 here have feedback. The other 2 don't have feedback. So we can't take the output of a particular pin and feed it back into the rules. And also in the data sheet, it actually shows how the differences between the different labels here. So 16L8 gives us our 2 dedicated outputs and 6 input outputs here. And this becomes important when we start to look at the output enables, in that when a pin like this has output enable disabled, then in fact it becomes an input. And this is from the monolithic memory. So monolithic memories were the company that actually first created PALs, and in fact created PALASM. And in this programmer logic handbook, there's a lot of background information, all sorts of information on logic rules and things like that. And for this 16L8, it also shows that in fact for our outputs, we have 8 outputs, but only 6 of them have this feedback here. 2 of them at the end here don't have the feedback. So in order to convert these files, we need to download CUPL 3.2 for DOS. So there is a link here, which I'll include in the description below. Extract the PTOC.EXE, run up DOSBox, and actually then run this command against an example file. So I've renamed the files that I had previously as PALASM because the PTOC utility automatically works with ASM files. And this should generate our PLD design file and also the SI file which is needed for the simulator. There's one extra thing we do need to worry about, in that PALASM would allow minus signs in the variable names, whereas CUPL doesn't like minus signs in the variable names. So we do have to convert any variable names that have a minus sign into something like an underscore. So we'll just have a look at the file we're going to use first of all. So this is a win merge of the file I've got here locally compared to the one that is in GitHub. So these have already been put up on GitHub, and you will notice there are a few differences. So one of the things is we have to take off the extra A on the end of the PAL definition, otherwise it doesn't work. And there were a few corrections in here. So one of the common problems with the PDF scanning of here is that quite often ones, I's and lowercase l's get confused, and so there was actually a lowercase l I think here. So it's just a few things to be wary of. I will update all of the PALASM files up on GitHub at some point in time to correct any of these minor things here. So I've got a copy of the file here. We're going to have a look at it in Notepad++. So you'll see this has already been done. So the first thing we're going to do is to get rid of our minus sign. So if we just use replace on the ones with the minus signs, and we'll put underscores in there. Okay, so we've done that conversion, and you'll see here that we've got a list of the pins at the top here. So this is a 20-pin chip. So we've got ground on pin 10 and VCC 5 volts on pin 20. You can see this particular one has the if condition. So basically this means if test is low, then this will be enabled. If test is high, then this output will be 3-state, will be disabled. So we've got all these conditions here, and you'll see that in PALASM, then in fact the inverted pins have the slash here. The AND condition is a star, and the OR condition is a plus. And then down here, the function table defines the simulator columns. So not all the columns above have to be in here, and they don't have to be in the same order. And one of the things which is a bit confusing is that some of these will have the slash in here as well. Now generally, whether the slash or inverted pin here and inverted pin here, it's not too bad. But when you have one up here which is not inverted and one down here is inverted, the rules can get a bit difficult to understand. And you'll see here we've just got the line of dashes here which are needed actually in the file format, and that we've got for inputs low and high and outputs low and high. Now, PALASM doesn't distinguish between the inputs and the outputs, and when we're converting this into CUPL, you'll see that this is actually one of the areas where I've had a few problems. And then the description down here just gets included in the comments. So let's go over to DOSBox. I'll just go to full screen on this. Okay, so I've got one file there that we've already looked at, and that has had the variable names changed from minus signs to underscores. So now we just do PTOC. That has converted them. So if we now go back and we'll go and check on those. So we now open those files. You can see that we've got the PLD and the simulation input file. Now you see it's just put some placeholders for some of this information. So these files do need to have a bit more information added to them. And this is the PLD file. You'll see that it's put all the pins in, it's put exclamation marks for all those with active low. And you'll notice as well that the pin 11, which is the output enable pin, the test pin, that is actually active low there. And you'll see that one of the problems with the conversion is that where there are comments on the line, then in fact it does wrap the last variable on the line before the comment down onto the next line. And you'll see that where we've got these OR terms, that really those would want to be on the next line. So the formatting does require a bit of tweaking to actually get right. But in fact, the only thing we actually have to get rid of is there's a stray semicolon in there, and that will then be correct. So if we go into WinCUPL, we're going to create a new project file. We need to make it an ATF16V8, which is the 20-pin version of the chip. And we need to include a WCP file. Now, I have found a few more limitations with these project files. They don't use relative paths, they use the physical path. So if you move a project file to another machine or another folder, then it won't work. Or you'd have thought they might want to do relative paths from the project file location, but unfortunately it doesn't. So the projects really aren't very useful, but they are necessary in order to be able to do this. So we just need to make sure the compiler options have the documentation output. Minimization is just quick, optimizations are turned off. I did find one or two of these had problems when optimizations were turned on. So we'll compile this. Compiled successfully. If we just look at the documentation file, so you can see you've got all of the rules, the table. We don't appear to have any zeros in there, so all of the pins seem to be correctly assigned, and we've also got the pin layout down at the bottom there. So if we have a look at the SI file, the simulation file now, so you'll see that the test is actually positive. It doesn't have the negative exclamation mark on there. And when we actually have a look at the vectors down the bottom here, you can see that in fact you've got zeros here and a 1 for when output is disabled. And when the definition in the simulation is different from the pin definition, then that can actually cause some problems. That did cause some confusion. So it's just something to look out for. If you've got a column that's got an exclamation mark in there and also in the test, then generally you won't have problems. But what you can see here is that for all the inputs, we've actually got 1s and 0s, but there's a couple of columns here that in fact have not been converted properly. And there's also another column here that isn't done properly. So we're just going to get rid of these extra dashes, which you don't need. Now, there's a nice feature in Notepad++. If you've got the column ++ add-in, this will actually allow me to do searches and replaces in column mode. So if you use the Alt key as we select, and then we go into the columns ++ search, we can actually change low to 0, high to 1. Then if we go to the last column here, 1 to high, 0 to low. Okay, so there is a little bit of fixing up these files before they'll convert properly, and it does require a bit of a round robin, compile it, find a problem and go back. But now I've converted all of these, then this hopefully should now work. So if we now do simulate, that has now produced a simulation file that has the inputs to the simulation, like the rules and the column names. The SO is the thing that we really want to look at. The WO is used for output into the graphical tool that came with the earlier version of WinSim. And you'll see here that the output here is okay. There's no error messages here, but it doesn't look particularly clean. And what we can do is if we go back into our simulation file, put a comma %1, and we do this for every column, we'll just add spaces. An extra 2 spaces there. And in fact, there is a semicolon there. The semicolon is actually down below the comment there, but it's generally easier to put it there. So now if we rerun the simulation, we now should have a slightly nicer output. Now we look at the output there, you can see this has actually produced a much better output. And in fact, if we open this in here, we can see if we compare this to the SI file and also to the ASM file, it makes it a lot easier to actually compare these things. Now, there's one other thing that we need to look at as well. The JED file is the JDEC file which is used to program the chip. And in fact, when we ran the simulator, what it's also done is added in this section here, which are the tests. In one of the earlier videos, I did show how to convert this. What we'll do is we will convert this into an XGPro test import file so we can actually test the physical chip once we program it. So we need to copy the test vectors from the JED file into YAML. We need to change the ends for the pin 10, which will be the ground pin, to G's, the ends for the power pin on pin 20 to V, and if there's any ends, we need to change these to X. If we miss these out, then you'll get an error when we convert the files from one format to the other. So let's open the JED file. You can see down here, this is the section that we need to be using. We use the Alt for doing a block there. And I have got a YAML file that I've already got here. They're very simple files. But you'll see here we've got the number of pins, VCC is 5, and then the vectors go here. And so I'm just going to paste those vectors in. Now we need to do the column changes that I told you before. So the N here, this needs to be changed from N to G for ground. Then pin 20 needs to be converted from N to V. Then finally, if there's any ends, we just need to see if there's any ends. No, there's no ends, so that's okay. So if you forget the ends, then the conversion will fail. So that is our input file for this XG logic test utility. So I covered this earlier. This is the link for it. We build this in Windows Subsystem for Linux. Now this is the command line that I used in one of the earlier videos, but I've already got this set up. This should be the command line. That's worked. If we just do, and this should have created it actually in our DOS PALASM folder. In fact, we can see here, so this file, the LGC file, is what we can use to import into our programmer. So I'm just going to run up XGPro. Now I've got the ATF16V8B already selected. I have actually got a chip in there. You can see this is the T56 programmer. This is the high-end programmer that's been replaced now by the T76, which I covered in some of the earlier videos. The USB cable is a little bit loose here. So I'm just going to read this first of all, and we'll erase it. And we're going to load our JED file. Unfortunately, the programmer doesn't read the tests in the JED file directly. Okay, so that's programmed the chip successfully. Now what we can now do, you can see we can now import that LGC file. That has imported one chip. We can see we've got a D4 SDEND, which is the chip that we're just using. And you can see that all these rules have come through. And now if we run test, we can now test this and it all comes out nicely. So it's actually passed. So this has actually managed to show that we've been able to take the data in the Compaq DeskPro internal design document for the programmable logic PAL definitions and actually program the chips and also test them. Now, a few problems on the way. Nothing was ever as simple as you might think it would be. And there were a couple of the conversions I really just couldn't get working. I went through this process even to programming the programmer to see if it's related to problems with the simulation conversion itself. And you'll see here that I was still finding that there were tests failing. So you see here on this particular one, I was having pins coming out that should have been high were coming out low, etc. And I spent quite a long time looking at this. So this is one particular one, the SCMDD, and this other one, the SCUPL as well. Now, what eventually I managed to get to the bottom of is that when looking at one of the other files generated, so it's a Berkeley format output file that's generated by CUPL, and what that indicated is that there are a number of the pins here which are both inputs and they're also outputs. And in fact, what the problem worked out to be is that in fact on some of the more complicated chips which have an output enable term, when you have an output enable term, when the pin is disabled, then some of those pins can actually act as inputs. So if we have a look, and this is from the datasheet, you can see here that for some of the pins on the end here, you see there is no return value. So you can't take the output value here and feed it back into the programmable matrix here. And you can see here in orange is where we have the output enable term. This one here with the green has actually got, when the output enable is set so that the output here is disabled, then this just acts as an input. Now the problem here is that when we were looking at the original ASM files, and PALASM didn't have any difference between an input and an output, it just said low or high. However, in our CUPL, we've got ones and zeros for inputs and we've got highs and lows for outputs. And what it turned out was, in fact, for this particular PLD, because it had output enable terms for some of the pins, in particular the X address 0 and the bus high enable, actually had output enable terms which were linked to all the other pins, which was quite a confusing situation. And in fact, what it turned out to be is there are some of these pins here, sometimes they needed to be ones and zeros and other times they needed to be lows and highs. Now because the output enable for these particular pins was not just tied to the output enable pin here, then in fact it was quite complicated to get to the bottom of. And there was also one other more complicated problem in that this particular logic here would fail with unstable outputs, the simulator. And in fact, what I end up having to do is to make this a latched output and using the bus address latch enable as a clock to actually do this. So this was one that actually needed quite a bit more work to do. But the primary issue here is that where we have columns that can be both inputs and outputs dependent on the output enable terms, then we need to make the inputs ones and zeros and the outputs lows and highs. So once I've managed to do this, then this all actually worked. And so we now have all these folders now have all the output files, so I'll be copying these up onto GitHub. So anyone who wants to have a look at this stuff for themselves, then you can do so. And in fact, from the more recent ATF16V8B, you can again see that when the output enable goes to be disabled, then in fact the pin can then go into the whole matrix here. So this is a potential problem that would occur with more recent chips. It's just that I haven't come across using the simulator before and needing to distinguish between the outputs and the inputs. When you've got an output, you need to put a high or low in your .si file. And when you've got an input, it needs to be a 1 or 0. And when you get the output errors in here, then generally, if you've got something which is high impedance, then you may very well find that with an error, then you may very well find you need to change a high or low to be a 1 or 0. Got to the bottom of that one. Okay, so in this video, we've managed to program one of our PAL chips. So we've gone from the PDF, converting it into CUPL, and doing all of the simulation files, and even not only programming it, but also then testing it as well. So now that I've actually done that for all of the PAL chips are going to need for this project, we should now be able to get on and start laying out the breadboard here. So in the next video, what I'm going to be doing is laying out a lot of the breadboards for the buffers and the latches to go around the CPU chip here. And we'll be using a lot of these programmable logic devices to wire all that up. So if you don't want to miss out on future videos, then please hit subscribe. If you'd like to put comments below, I do try and get back to you within 24 hours where I'm able to. If you could hit like, it just helps to make the videos available to more people. Thanks for watching.